Hi, I'm Cassidy Curtis, and I'm here to talk about the steps we're taking towards believable acting for autonomous animated characters. I want to start with some important context and define a few terms. There's something we all do when we experience any kind of fictional character. It's called suspension of disbelief. You know the character's not real, but you choose to believe in it anyway. How the character behaves can make a huge difference in your ability to do this. As long as the character's behavior stays believable, you can stay immersed in its story and you can see the world from its point of view. But if its behavior becomes unbelievable, you risk being popped out of the experience. To create a performance that sustains the viewer's suspension of disbelief means having control over every aspect of the character's behavior, from the physical to the psychological, in a way that reveals its inner life. And the craft of creating such a performance is what we call acting. So, why pursue acting for autonomous characters? Well, in linear media like movies and TV, the job of acting is handled by human actors or animators. But in interactive media, when the characters have to act autonomously, the acting is rarely strong enough to sustain the viewer's suspension of disbelief. And this is because autonomous acting is a really hard problem. So we tackle this topic in two parts. First, a set of design principles that we think contribute to the believability of a character's acting performance. And then we have a simple autonomous character that implements most of these principles using machine learning and procedural animation. Now, we're certainly not the first to take a crack at this problem. Ken Perlin and colleagues pioneered the use of procedural animation to express emotion and personality through movement. But to make an entire believable performance, these digital actors still needed guidance from a human director in the form of wiggling sliders or text input. So they weren't strictly autonomous, although that was the aspiration at the time. Meanwhile, others were working on truly autonomous agents. Breitenberg showed that even simple deterministic vehicles could create the illusion of having emotions and desires. And Joseph Bates proposed that believable autonomous characters could be achieved with a combination of AI and animation techniques, and which is something we agree with. And Loyal fleshed out this idea by breaking down believability into more specific parts. Later, Stuart Wilson proposed the idea of an animat, which is an agent whose behavior emerges from underlying motivations. Our system is in many ways a descendant of all of these ideas. Our system also builds on a body of work in emotion and motivation systems in machine learning. Where our work differs from most of this previous work is that we're really focused on delivering believable acting results. Now, I said that believable acting in games is rare, but there are some really great examples out there. In the game Red Dead Redemption 2, the horses have a utility-based motivation system that drives their autonomous behaviors. And in The Last Guardian, the character Trico combines scripted behaviors with procedural and handcrafted animation for locomotion, attention, and physical simulation. And both of these characters are quite believable to the extent that players can form a strong emotional bond with them over the course of the game. Hopefully, this talk will give you some tools to better understand why these characters work so well. So let's move on to the first part of this talk. What do we even mean by believability? Well, here's how we define it. It's a viewer's assessment of a character's observed behavior as measured against the viewer's expectations of its capabilities. Now, observed behavior, that's important because it turns out it doesn't matter so much what the character thinks or is capable of thinking. What really matters is what its behavior tells you about what it thinks. And then the viewer's expectations depend on several other factors: the visual design of the character, the viewer's prior beliefs about that type of character, and the rules of the character's world. Let me show you an example. So a character's appearance affects the viewer's expectations. If your character looks like this, you might expect it to speak and wear clothing, but not if it looks like this. It also affects our expectations about the rules of the character's world. If you were to drop both of these characters from a great height, you'd give them very different prospects for survival. So breaking a character's believability even briefly can undermine the viewer's experience. You may come in willingly suspending your disbelief, but once you've been popped out of the story, it can be hard to reconnect. Believability is also highly context dependent. An action that's believable once might not be believable if repeated over and over again. So you have to think about maintaining believability across all timescales from a fraction of a second out to the duration of the entire experience. And this is tricky because it turns out viewers have all kinds of different expectations about characters. And that means the illusion that we call believability can fail in many different ways. So what are those ways exactly? Well, psychologists, animators, and HCI researchers have all spent time on this, and we've pulled together ideas from all of these fields, and we've compiled them into a list that we call principles of believability. These are all attributes of a character's observable behavior, and the idea is that you could use these as design guidelines as you develop your characters. In the interest of time, I'm going to focus on the first 9 of these, since that's all our system was designed to robustly demonstrate, but you could read about the rest in our paper. So let's dive right in. Principle 1, coherence of identity. A character should maintain consistent characteristics over time. A common violation of this principle is when you let a different algorithm take control over animating a character. For example, cutscenes versus gameplay scenes in games, or when your playful toy robot suddenly transforms into a digital voice assistant. A character should obey physical laws consistent with the rules of its world. I say its world because the rules of its world may be different from our world, but that's okay as long as those rules are internally consistent. Biological movement. Our brains are hardwired to perceive and interpret biological movement. A lot of Disney's principles of animation, things like squash and stretch, overlapping action, arcs and spacing, exist largely to support the illusion of biological movement. Self-propulsion. A character should seem to appear to move on its own initiative. Self-propulsion is a precursor for the perception of agency, even in infants. Things that violate this principle include things like marionettes, if it's too obvious that something else is pulling their strings. Contingent interaction. A character should react to events in a way that clearly demonstrates the cause and effect relationship it has with its environment. A very common violation of this in games is when a character's motion is built on pre-baked animation clips. While one of those clips is playing, the character isn't really responsive to its environment. Self-motivation. A character should appear to be acting on its own internal motivations and pursuing its goals to satisfy its needs. It turns out that even simple shapes like these dots will be perceived as having agency and animacy if they appear to be pursuing goals. This has been demonstrated even in 1-year-old infants. In this particular example, these illustrations are a reproduction of illustrations from an experiment by Gergely and Chibra, as you see below. The principle of attention. A character's attention gives you a window into what it can perceive, what it's thinking about, or what may be important to it. And to satisfy this principle, what a character pays attention to needs to be appropriate to its situation and legible to the viewer. This is most often shown by making a character look at something, but it can also be shown by listening, smelling, or feeling. The principle of attention applies across all the senses. And now we get to the principle of emotion. Note that almost every aspect of a character's behavior can convey information about its emotional state. So its choice of actions or inaction, modulations of those actions like how quickly it moves, or explicit display of emotional affect like posture, facial expression, tone of voice. For an emotion to feel genuine, all of these aspects should be consistent with each other. And now we get to explainability. Explainability is that the character should behave in a way that lets the viewer form an explanation consistent with the observed evidence. Explainability is about understanding why a character is doing what it's doing. And this principle, in a lot of ways, depends on all of the others. In the example you see here, when you remove attention and emotion, you deprive the viewer of the evidence they need to explain what they're seeing, and the character's actions become unexplainable. I'll whiz through these last few because we don't go into them in great detail in the paper, but the principle of thought, a character should show evidence of mental processes like deciding and planning. Sociality, that a character should have a mental model of other characters and act on them. We're social beings and we expect sociality from beings like ourselves. Personality, that a character should have unique behavioral and expressive traits that distinguish it from its peers. And lastly, change with experience, that the character's behavior shows the effect of its past experiences. Change in behavior shows that those experiences were meaningful to the character, and this has also been shown to impact the viewer's ability to empathize with the character. So that's all the principles. I want to stress that this is not a recipe, but it's a set of guidelines. And each of these principles applies only so far as the viewer's expectations require it. So if your character is, say, a photorealistic squirrel, you might not expect it to show much evidence of thought. And if it's a robot, you may not expect much biological movement. And again, for our implementation, we've focused on these first 9 principles. So now let's talk about what we've built to demonstrate these principles. We've built a system to animate an autonomous character using reinforcement learning and procedural animation. The core idea is that everything about this character's behavior should emerge from the same underlying set of motivations. We've started with the most basic physiological motivations, things like safety and nourishment. These are needs that all animals share, which we hope would make them universally relatable to human viewers. And here's what our character looks like. Its name is Asho. We chose this design because it sets the viewer's behavior, the viewer's expectations appropriately. It's a quadruped, which sets certain expectations for intelligence. It's an imaginary creature, so the design is honest as to its artificial nature. And since our focus is on the animation, we've removed any details that might distract the viewer from that. Asho's environment has a variety of elements that can impact its needs in different ways. There are dangerous cliffs that can impact safety, food sources to provide nourishment, and critters, those little pink triangles, that can attack Asho, but also compete for food. So let's take a look at how Asho behaves. Asho acts on its own motivational drives, seeks out food and avoids danger. It pays attention to whatever's most emotionally relevant to it at any time, and it anticipates the future, and if something unexpected happens, it gets surprised. All the behavior that you see here is driven spontaneously in real time by signals from its reinforcement learning brain. So how does this work? Well, let me give you an overview of the whole system. So reinforcement learning lets an agent learn to take actions that maximize the reward that it gets from its environment, and our system extends this concept in a few ways. We have multiple motivation drives: safety, nourishment, and rest, each of which has its own separate reward function. And then we train a value function, also using machine learning, to predict future accumulation of reward for each motivational drive. Together, these allow us to generate emotion signals representing how the character feels about its current state and future prospects with respect to each motivational drive. It also lets us generate attention signals by identifying the object that's most emotionally relevant. The RL brain sends all of these signals to a procedural animation system that expresses them as continuous, responsive, biophysical movement in real time. Each of these components adds support for one or more of the believability principles, and they work together to support explainability. Now, let's take a look at how these simple parts work together to create complex behavior. Things get really interesting when there's conflict between different motivations. Here, Asho feels positive nourishment anticipation because it's hungry and it sees this fruit. But when it sees these dangerous critters approaching, its attitude changes from hopeful to apprehensive because it anticipates a decrease in safety. And eventually the brain's action policy decides it's best to look for food somewhere else. Asho also has a simple model of the user that depends on the user's behavior. It starts out somewhat fearful of you, but if you treat it well by feeding it, its attitude towards you will change. And this lets us explore in a rudimentary way the principles of sociality and change with experience. So that's our overview of the whole system. Now let's dive into how each component works in a bit more detail. So why use reinforcement learning? Well, it inherently supports self-motivation since it's driven by the motivational drives, and also change with experience because the character's behavior results from the experiences it had during training. But also it lets us produce complex emergent behaviors from simple components, and it's agnostic to the design of the character and its environment, so it can easily adapt to changes in either. The motivation system has 3 scalar value drives: nourishment, safety, and rest, and each drive has a set point that it returns to and a decay rate that controls how quickly it gets there. And then discrete events that happen affect each drive's values. So, for example, eating food increases the nourishment drive, and being attacked by critters decreases safety. And then finally, there's a piecewise linear function that maps each drive value to the reward incurred by the RL brain. How does the RL brain perceive its environment? Well, the character has 2 types of sensor that are meant to represent at an abstract level things that an animal could plausibly perceive. These sensors are anchored to the character's base node, so they're not affected by the animation of its head or body. So first, there's a ray tracing object sensor that detects visible objects within the character's cone of view. If an object is occluded by rocks or hills, the sensor doesn't report it. But the sensor does retain a memory of the last known position of any object that's recently passed out of view. Then there's a navigation sensor that detects boundaries of the world's navigation mesh and reports whether it's possible to jump to another part of the mesh. And this is how the character is able to make sense of its physical environment. On the output side, the brain outputs an action vector consisting of 6 real values. The first 2 control continuous actions, moving forward and back and turning left and right. These continuous actions can range from fast and intense to slow and subtle, and that's why we use floating point values for that. The other 4 control discrete actions: grabbing an object, dropping the object you're holding, eating what you're holding if it's food, and roaring, which scares away approaching critters. And the brain makes decisions and produces these actions at a rate of 5 times per second, which lets it respond swiftly to changes in its environment, supporting the principle of contingent interaction. To generate emotions, the brain uses the current motivational drive values and the predictive model to produce 3 kinds of emotion signals for each drive: immediate emotions reflecting the current reward value, anticipatory emotions based on the predicted future reward, and surprise based on the derivative of predicted reward. To generate attention signals, we use a kind of counterfactual observation. We go through the list of currently visible objects in the observation vector and remove one at a time, and we run each modified observation through the value predictor and then measure the difference in the predicted rewards. The object that has the largest impact, positive or negative, on predicted reward becomes the new target of attention. So the brain can generate all these signals, but we also need to express them in a way that supports the principles of believability, particularly the ones highlighted here. That's the job of the procedural animation system. Now, there are many different procedural animation techniques you could use for this, but whatever technique you use must meet at least these minimum requirements to get believable acting out of it. Our approach is to build up the overall movement from several independent layers that run concurrently, each of which can respond immediately to changes in the brain's signals. This lets us produce a wide variety of behaviors from minimal handcrafted input. In fact, less than 30 seconds of hand-animated source clips were used in total to generate all the animation you see in this talk. So let's take a look at those layers. The gate system lets Asho smoothly shift between quadruped gaits as it changes speed, and the gaits themselves are handcrafted by an animator to caricature the movement patterns and weight shifts typical of each gait. This supports the principles of physical and biological movement and also self-propulsion. The attention expression system aims the character's head toward the object of its attention and triggers a blink animation when attention shifts to a new object. These salient changes draw the viewer's eye, supporting the principle of attention legibility. The emotion expression system transforms the brain's fluctuating emotion signals into salient changes in posture, gait, and facial expression, supporting the principle of emotion legibility. And lastly, there's a layer of physical simulation, which adds overlapping action to Asho's headdress and tail. And this supports the principles of physical and biological movement, and indirectly also self-propulsion. So let's talk about the training process. We train our model using the PPO method with about 800,000 episodes, each one about 4 minutes long, for a total of about 55,000 hours of simulated time. This amounts to about 2 to 4 hours of wall clock time because we're running faster than real time and also running in parallel on multiple machines. We base the total amount of time we train for on the accumulated reward per episode, which you see in this graph. We basically stop the training at a point where that value starts to plateau. What's actually happening during training is the character is going through this curriculum of training environments, each of which is designed to give Asho a different kind of experience, producing enough variety of experience in total to develop the set of skills it needs to satisfy its motivations. We model the user by giving Asho a scalar-valued user score, which accumulates basic statistics of the user's actions. So helpful actions like feeding or petting increase the user score. Harmful actions like poking decrease it. And then the training curriculum includes simulated users that span this full range of possible user scores and associated behaviors. And this lets Asho learn different strategies for dealing with different kinds of users and also different emotions towards them. So to verify that the RL brain and this entire system is working as expected, we run it through a series of tests. Some tests can run automatically based on pass-fail conditions, like whether Asho can escape from a canyon, turn to eat food, or avoid falling from a cliff. Other tests are more subjective in nature. To test Asho's emotions, we created a series of scenarios designed to provoke interesting sequences of emotional reactions. Each time we train a new policy, we run it through these scenarios and evaluate their behavior, their believability visually. We call these tests emotional calisthenics. So as soon as we got Asho up and running, we started noticing interesting emergent behaviors. These were things that we never explicitly programmed Asho to do. They just happened. Before it learns to trust you, Asho will visibly hesitate between its fear of you, the user, and its hunger for the tasty fruit near the camera. But once you've earned its trust by feeding it, it will come right up to you and even follow you as you move around. And if you hide yourself from view, it'll step away. And when you reveal yourself again, it gets happily surprised. Users realize that they can use this to play peekaboo. Even when not much is happening at all, because Asho's actions, attention, and emotions all emerge from the same underlying motivations, its behavior stays grounded and coherent, which helps its acting feel genuine. So we were reasonably happy with these results, but we were also curious. How does Asho's behavior change over the course of the training process? Here's that graph of accumulated reward per episode. We know that if this value goes up, the character is improving, but what does the number really mean? To find out, we ran some tests using snapshots from a single successful RL training run, and here's what we saw. It turns out that Asho acquires different skills at different times. By 3% of the way through, it's already learned to avoid critters, but it hasn't yet learned that it can get nourishment by seeking food. Note that it also shows no positive emotions about food. This is because its emotions emerge from the same value predictions as its action policy. By 25%, Asho's learned to seek out and eat food, and its emotions also show positive anticipation when food appears. But if critters are present, it seems much more fearful and it won't seek out food. By the end of training, Asho has learned how to get nourishment while minimizing harm from critters, and along with that skill comes a bolder attitude toward the critters. We think this shows really interesting potential for how even a character's personality could be emergent from the RL training process. We also did a user study with 50 participants to learn how people perceive our character. there isn't yet a standard instrument for measuring a character's believability, so we relied on existing instruments like the Godspeed and Dimensions of Mind questionnaires. And users rated Asho as being capable of experiencing emotions like fear, hunger, joy, and pain, which we would expect given that it has the motivational drives of nourishment and safety. But interestingly, they rated it poorly on ability to experience embarrassment, which also makes sense because to experience embarrassment, a character would need to have some social model of other people, which we did not equip our character with. So to sum up, we've built this system around these basic physiological drives, but we think that this intrinsically motivated approach should generalize well to other kinds of motivations. So we're very interested in exploring that. For future work, one direction worth exploring is also to develop better instruments for measuring believability directly. And another would be to develop systems that can demonstrate these last four principles in a more robust way. So on behalf of the whole team, thank you very much for listening.